This is Representing Relations, a knoatom.com video, brought to you by TJ Bierce, Matt Berger, Zach Houston, and Ryan Kreider. There are many ways in which relations can be represented. However, the most prominently used way is through a matrix. This is known as an adjacency matrix on a set. This is an m by n Boolean matrix like the one below. You'll see that what it does is it takes the elements in a set and compares them against each other. If an element has the relation against another element, you will see a 1 in the matrix. Otherwise, you will see a 0. For example, if you have the relation less than or equal to, A is less than or equal to A, because A is equal to itself. So you put a 1. Now if B is also less than or equal to A, you will have a 1. This will continue throughout the entire matrix and will represent which elements have which relations compared to which other elements. With relations, you can have many properties. There are three main properties, however. These are known as the reflexive property, the symmetric property, and the transitive property. Here, we'll first start by talking about the reflexive property. The reflexive property is defined as an element in a set having a relation with itself. In other words, A shares a relation with A, B with B, C with C, D with D, and so on and so forth for every element in the set. This can be seen in a matrix by looking at the main diagonal, right here. What you'll notice is that the main diagonal represents A with A, B with B, so on and so forth. So if the main diagonal is entirely made up of 1s, then you know that the matrix represents a relation that is reflexive. However, if the main diagonal is made up of entirely 0s, this matrix represents a relation that is defined as irreflexive. Irreflexive is not the opposite of reflexive. Reflexive means every element is reflexive with itself. Irreflexive means every element is not reflexive with itself. So every element has a 0. If the diagonal is mixed with 1s and 0s, then that definition, or that has no definition. So that matrix relation is neither reflexive or irreflexive. Symmetry is defined as a set having a relation between A and B must also have a relation between B and A. So in other words, for every 1 in the matrix other than the main diagonal, there must be a symmetric pair that also has a 1. So if we look at the main diagonal, what we're trying to see is symmetry around it. Every element around the main diagonal has a symmetric pair that it partners up with. For example, AB right here, its symmetric pair is BA. So on and so forth throughout the entire matrix. Now, what it means for a property for a relation to be symmetric is that if AB has a 1, BA must also have a 1 for every single one in the relation. So if you look at this relation, you can see right away that it is not symmetric. There is another term known as antisymmetric. This property states that if you have AB and they are not equal to each other, then you do not have BA. This means that if you have AB right here and they're not equal, then BA must be a 0. Now, if you look at this matrix right here, you'll see that for every 1 outside of the main diagonal, its symmetric pair is a 0. This means that this property is that this relation is antisymmetric. The fact that you have 2 zeros doesn't matter. It just matters if you have a 1, you must also have a 0. This holds for a symmetric property as well. If you have all 1s, but these two are still 0s, that's okay. It just says for something to be symmetric or antisymmetric, if you have 1, you either do or do not have the other. If you don't have it, it doesn't matter with the other. If they're both gone, that's okay. The last property is called the transitive property. This property is hard to see in just one single matrix, but it can be easy to find if you find what is known as a transitive closure, which we will discuss in a moment. Now closures, which there are these main three that we will be looking at, reflexive, symmetric, and transitive, are what's known, or are the matrix that represents the relation plus any extra relations you have to add to get it to that property. In other words, if I have this matrix, to create a reflexive closure, I leave the matrix how it is, except if there's any zeros in the main diagonals, I make them 1. This allows me to add the least amount of elements I need such that I make the property, or I make the relation reflexive, and it still maintains the original relation within it. Symmetric closures are the same. If I have a 1 and I want a symmetric closure, I make its I make its symmetric pair a 1 as well. So for this one, you would have to add elements to each symmetric pair where the element is already a 1, and you would get a symmetric closure. Transitive closures, though, are a little harder to find, because if you fix a couple errors in a transitive closure, more create afterwards. So what it means for something to be transitive is that if A shakes hands with B and B shakes hands with C, A must also shake hands with C, otherwise the property is not transitive. Or if A can get to C by some series of paths, A must have a direct path to C. Now the problem is, if you have A with B and then B linked up with C, but let's say you have C linked up with D. Well, now to make it transitive originally, all you needed to do was create a pair between A and C. But now you have a D, so creating a pair between A and C means that you have A goes to C, which goes to D. So now you have to create another one because of the one you just created. This is why transitive properties can be difficult. So how a transitive closure is found is it is found by taking the union of all powers of the relation. Or you have the relation, like so, and then you Boolean OR it with itself squared, Boolean ORed with itself cubed, yada yada yada, all the way up to some m. Now when you Boolean OR a relation matrix, or an adjacency matrix, with itself squared, the matrix you get in return represents the number of length 2 paths from one element to another. So, if we were to Boolean OR this matrix with itself squared, if you find a 1 in any of the locations, what that means is that there is a path of length 2 from A to B. So it could mean that you could go from A to C to B to get there, or A to D to B, or anything. It just means that you can get to B from A in 2 steps. So now if you Boolean OR all the way up to infinity, this finds every possible path from one vertex to another. And this is what's known as your transitive closure. What you'll notice, though, is in most situations, you'll find a transitive closure in less than infinite Boolean ORs. This is because in most smaller matrices like this, you only have to Boolean OR with a few of its power sets before you'll get repeat matrices. In other words, if you Boolean OR this one with itself squared, you'll get a matrix. Now if you Boolean OR that matrix with the original one like this, cubed, you might get the same matrix. Or at some point you will start getting the same matrix as your solution. This means that the time before the recurrence happens is where your transitive closure exists. Relations can also be represented through graphs. Now there are various types of graphs that represent numerous different relations. You have undirected graphs and directed graphs, and how these are different is an undirected graph is a solid line between vertices. This means that A has a path to B, and B also has a path to A. Undirected graphs are usually used to represent symmetric relations, as all it means is that one line shows that these two elements are symmetric to each other. So if you have a graph of vertices all connected with just lines, so if you have an undirected graph, that means that that graph represents a symmetric property. A directed graph, however, is two vertices that are connected by an arrow. This shows direction, meaning that A relates to B, but B does not relate to A. You cannot go opposite the direction of the arrow. You can also have weighted graphs. A weighted graph is either a directed or undirected graph represented with a number on the edge. Now this number can be any sort of thing. It can represent the number of steps from A to B or the distance from A to B. All it is that you have some number that has a representation that shows something from A to B, or any other vertices on the graph. Then finally, you can have simple graphs. There are many other graphs, but these are three of the main ones that we will look at throughout the PowerPoint. Now you can easily translate an adjacency matrix into a graph. What this means is that anywhere in a matrix that you have a 1, this shows that A has a directed line from itself to each of these other matrices, or each of these other vertices. Now, lines to yourself, or reflexive lines, can be represented in a number of ways. For example, I chose to represent them in this graph by a closed circle. Because this circle is filled in blue, that is how I say that A has a path right back to itself. Now, if one of these didn't have a path to itself, I would represent it by an empty circle with just the letter in it. Most people, however, use an arrow similar to these that just curves around and comes back to show a circular path just going to A. Now, to tell if a graph is reflexive, all you have to do is look at each vertice and see if it has one of those paths. If not, it is not a reflexive graph. The same thing goes for symmetry. If, like I said before, if you do not have a directed graph, it is automatically symmetric, because undirected graphs represent that A can go to D and D can go to A. In a directed graph, however, though, if you have an arrow one way, you have to have an arrow going back for it to be symmetric. So this graph is not symmetric, because there are no arrows going back from where these arrows point. And then finally, transitivity is relatively easy to spot in smaller graphs like this, because you'll notice that all you have to do is look at paths. So you see if A goes to C, C goes nowhere else, so you're good. Now if A goes to B, B goes to D, which means you need a path directly from A to D for the graph to be transitive, which we do. And that's all that you can have in this graph, because D goes nowhere else and B only goes to D. So there are no other possible transitive paths that we're missing. Thus, this graph is a transitive graph. You can also tell closures on graphs as well. For a reflexive closure, you just look, as I said before, at each vertice and see if it has the reflexive property, depending on how the graph represents the reflexive property. So in this case, it does. For a symmetric closure, the same thing. If they have arrows back, and make sure that each one has an arrow back. If it doesn't, add it. That way you have an arrow, that way you have a circuit between two different vertices. And then finally, for transitive closures, these can be relatively easy to find on small graphs like this, but when you get graphs that are representing large sets of data, it can be very difficult to actually use a graph to find a transitive closure. In those situations, you would want to use a matrice and use composition like we did before. Hopefully this helps you better understand relations and how they can be represented. Also, the properties that represent relations. This was a KNO Atom video